Oh yeah. Also, sorry for missing that email. I apologize.
That's fine. That's fine. Because I know sometimes if your email's not connected to your phone, then unless you're on a computer,
Yeah.
we wouldn't know that you've got an email. No problem.
I can give you if you want. I can next time you can just like text me. I'll give you
No, that
my
would be easy actually.
yeah.
Yeah.
I'll give you my number and then you can
Yeah,
just
we're gonna
text it to
exchange
me.
numbers. That I was just about to suggest that, but you got there
Yeah.
before. That's great. Yeah, I'll definitely do that. But
All
cool.
right. Yeah. I'll write it up
No
after I
problem.
finish this.
That's fine. That's fine. We got time. We got
Check
time.
this correct. Would it be they have the same displacement?
They have the same displacement indeed. Very good. Okay. Next one, number 2.
Distance. Would it be the slope of the velocity time?
Correct. Absolutely.
Graph?
Spot on. Good. Next one, number 3.
About the motion. Could you say the speed changes?
Just say that the speed changes. Yeah.
Or it
Yeah.
starts from rest. No, so it's either I think it's either B or D.
B or D. Just have a little bit of a think then and weigh
Okay.
options between B and D.
It says about the motion, which I guess isn't. Oh, the speed does change.
Yeah.
Yeah, the speed does change. Is it D?
So the speed changes. And we're told that, okay, at time 0, so it does, well, it's a very, very tricky one. It really, really is tricky. So if I look at the gradient of this, what would this be giving me, the gradient of this?
That would be speed.
That will be the speed.
Distance over time.
That absolutely. So here, when you say it starts, is it possible to say that it starts from rest if we really think about it?
Yeah.
If something starts from rest, it means that its initial speed is what?
0.
Initial speed is 0. Correct. What is the initial speed of this? Well, what is the initial speed represented here?
It starts at the origin.
Yeah,
So I guess it's the 0.
it starts off at the origin, but when it starts off at the origin, it starts off at the speed already. Does that make sense?
It starts off with the speed.
Correct. Yeah, it starts off with, with
Okay.
an initial speed already. And how do we know it starts off with an initial speed? Well, the gradient of this line is constant. So the speed here is the same as the speed there. It's the same as the speed there. It's also the same as the speed there.
Oh, yeah.
It's a very tricky one. Okay.
Makes sense. Yeah.
Yeah, very, very tricky. But that's the whole point why we want to go through this. And at which point then, having just gone through that warm up, I'm going to ask you, so did you have any particular elements you want to touch on within motion forces, or do you just want firstly us to go through a whole general overview, make sure that you don't miss out on any basics?
Yeah, I was sort of looking at
Yeah,
collisions, elastic and inelastic collisions.
yeah,
And I would say also sort of turning forces.
collisions. Yeah, so both elastic
Yeah, and like moments
and inelastic. Okay, and the other one was moments. You said
turning forces and like moments. Yeah.
moments. Okay, all right. So not so much on directly to do with motion or projectile motion or any of those kind of things.
Yeah, and also and one more. As you said, yeah, projectile motion is
Okay,
yeah.
and projectile motion as well. Okay, so we can touch up a little projectile motion. Okay, there is enough here. We'll try and start off with one topic and see if we can be afforded time to maybe start another one as well. Yeah, but we'll see what progress we make. Okay, so maybe it might make sense to start off with projectile motion, seeing as most of the examples we were looking at were relating to motion. So just a few key things here and a few key ideas, which I'm sure you know, but just to make sure that we're starting off on the right footing with this. Whenever we're dealing with quantities, especially when we're dealing with this topic, quantities will either have to be or will be divided into either scalars or vectors. Can you tell me what the difference is between a scalar quantity and a vector quantity?
Yeah. Scalar quantities have magnitude and vector quantities have magnitude and direction.
Correct. These guys have magnitude plus direction. Correct. So in essence, we can think about vectors as being two-dimensional. We can think about scalars as being one-dimensional. So the main scalars you need to acquaint yourself with are those of distance, at least with relation to this topic, distance and speed. Can you think of any vector quantities examples?
Velocity and displacement.
Velocity, correct. Displacement, correct. Any others?
Acceleration.
Correct. Acceleration too. Now let's just look at formulas we use to calculate some of these things. So what's the formula for speed? Can you remind me?
Distance over time.
Correct. Distance over time. And formula for velocity?
Displacement over time.
Correct. Displacement over time, or rather, we normally say the change in displacement, isn't it? Or the change in distance over time. You're absolutely right. Displacement over time. Well, we can rearrange this. An acceleration
is change in velocity
correct.
over time.
Spot on. Change in velocity over time. Now, there's something I want you to notice. These equations here that we've written down here, very, very different. Or in other words, this velocity equation, to be more specific, is very different to this speed equation. Now, what's the key difference? Here, these are, or this equation we've written here, velocity equals displacement over time. This is a vector equation. Now, do you remember learning about vectors at GCSE in maths?
Yeah.
Correct. So
Yeah.
speaking, if I was to write this formula, I would say V, to show it's a vector, is equal to displacement, or the change in displacement, delta S, which is a vector, divided by time. Time is a scalar, so I do not need to denote that. It simply, if you like, scales the vector quantity which is displacement. Likewise, acceleration, strictly speaking, I know you won't see this notation, but these are vector equations. Now, why is it important to have that appreciation? The way you deal with a vector equation is slightly different with how you deal with these kind of equations where all quantities are scalars. Now, while we're at this, I want you to notice something here. A vector quantity divided by a scalar quantity always results in a vector quantity, because the scalar only scales the vector. It either shrinks it or makes it big. That's what a scalar does. Yeah. It gives it a scale of either making it small or big. That's all a scalar does. Likewise here, acceleration is a vector because this change in velocity is a vector and time itself is a scalar. And if I divide a vector by a scalar, I always get a vector. Likewise, as a general rule, if I multiply a vector by a scalar, I'll always end up with a vector. The scalar, as the name denotes, just scales the vector. So whether I divide it or multiply it doesn't change the result. The result will still be a vector. Now here we've got a scalar dividing by a scalar, and naturally the answer would also be a scalar. So that's another way in case you're given something that's a bit strange, you're not sure, is this a vector? And you ask the question, is this a vector or is it a scalar? Yeah, just as an example, momentum. Momentum is mass times velocity. Yeah, that's a scalar. Velocity is a vector. A scalar times a vector will always result in a vector. So momentum must be a vector. Okay, excellent. Okay, so now with that understanding done, all right, maybe just a little bit of we can go into projectile motion. Actually, we can go straight into it.
Yeah,
dive straight into it. Right, so the famous Suvat equations. Suvat, look at a bit on Suvat here. And the key thing is, because these are vector equations, we need to use appropriate signs to indicate direction, to indicate the direction of the vectors, to indicate direction of vectors. That's the key thing first and foremost. So, of the Suvat equations that we know, what is it that we know firstly? One of the key things we need to understand is that if I have, or if you have a velocity time graph, like so, if we have a velocity time graph, and we have some initial speed or velocity u, by the way, not and we have some final velocity v. All right, so that's velocity in meters per second, and this here would be my time in seconds. Now, what does the area under this graph represent?
would that be the displacement?
You're absolutely right. So area represents displacement. Okay, excellent. So what shape is this? If I want to find the area, what formula might I use? What shape is this?
Oh god, I'm so oh god, what is it?
I know it's been time. It's been a long time, hasn't it?
Yeah, it's been a long time since
It's a trapezium.
I was gonna say that. I said
You were there because you started up with
I didn't follow through.
He knows what it is. Yeah, it's a trapezium. You're absolutely right. Not that you need to remember it, but can you remember how to find the area of a trapezium?
Absolutely not.
No problem. No, that's fine. This here, okay, trapezium area is given by half a plus b Now, this sum here would be the sum of the parallel sides. So this side is parallel to that side. So it's that length added to that length multiplied by the height, in which case this would be my height here. So let's imagine that this here is at a time t. Yeah, so I've got u, v, and t over here. If I want to find the area, which is the displacement s would be half. Well, parallel sides, this side here is only u units, and this side here is v units. That is v where it stops. So I would have u plus v multiplied by the height, which is t. Okay? So these are vectors. All right, so I've got s equals half u plus v multiplied by the time. All right, what other equations do I also know? Well, what is this? This quantity here, initial plus final velocity, what does that represent divided by 2? U plus v divided by 2, just this part here, what does this represent? Any ideas?
Divided by 2.
Not sure?
With that, no,
yeah.
not sure, no.
Yeah, okay, so this here represents average velocity.
I see.
Okay, so you add the two velocities and divide by 2. Now, of course, if the initial velocity is equal to the final velocity, then you would have two quantities that are the same. So the average velocity would just be one constant value. Does that make sense so far, right?
Yeah.
Excellent. Okay, so what other formulas do we know? So we've got S equals half U plus V times T. This is quite an important one. Any others that we can derive? We also know something about acceleration, don't we? We know that acceleration is equal to V minus U over T. That makes sense so far? Yeah?
Yeah.
Acceleration is V minus U over T. So we can, of course, play around with this equation because we can substitute what T is, can't we? So this gives us something that says that T is equal to V minus U over A. Now, I will not include the bars there to show that it's a vector equation because we all appreciate that now, but it's just a point to emphasize. So I can rewrite this now. I can sub my T and put V minus U in there, can't I? So I can have S equals half U plus V multiplied by time, but this time around, I'm going to have V minus U over A for the time, okay? Now, it's probably many moons since you did this, but here we can play around with these mathematically because they're opposite signs. So it's like one of those x minus 3, or rather x minus y and x plus y. If you expand that, yeah, if you multiply all these brackets together, this is a special case because it's the same variable, but opposite signs in the other bracket. This always simplifies to x squared minus y squared. This is something you'd have learned at GCSE, yeah, and this is called completing the square. No, not completing the square. A difference of two squares, I beg your pardon.
Yeah.
This is a difference of two squares. It's a mathematical concept and it's very important, especially when you start dealing with some slightly advanced stuff in your second year. So this is worth remembering, that little difference of two squares. So of course, then using that knowledge, this can be simplified to give S equals to V squared minus U squared over 2A. And so we can have another formula now that says that, yeah, we can rewrite this to say that V squared is equal to U squared plus 2AS. Yeah.
Yeah.
So far, so good. Now, we could also have manipulated this equation as well by making V the subject of the formula and plugging it into there, or U the subject of the formula. By doing those manipulations, yes, we would end up, and I'll leave that as a little bit of an exercise for you to try in your homework. Try and see if you can get to the derivation of this formula by making a substitution. Oops, where is this? There we go. S equals UT plus half AT squared. Okay, so that is the other main formula that we see. Yeah, and we've also got the V equals U plus AT. Right, so let's just first look at horizontal projectile, horizontal projectile. Even before we start looking at horizontal projectile, we're simply just going to look at how do we set up our equations. Let's just look at something thrown vertically upwards. Yeah, okay. Something is thrown vertically upwards, and let's imagine I tell you that it reaches a height of 27 meters. So that's my ball there, and it reaches a height of 27 meters. Now I ask you, that's the maximum height. So maximum height above throw point is 27 meters. Now I said, now I want you to tell me with what initial velocity. The question is, what initial velocity or rather, let's change this. With what speed, with what velocity was it projected? With what velocity was it projected? Now, the question like this, we need to make assumptions, and it's worth knowing assumptions when we're doing these calculations. Generally, the assumptions we'll make, can you remember any assumptions?
You'd with weight. So gravity, the acceleration of gravity.
Good.
Would you say there's no air resistance?
Due to gravity constant, which it would have to be, yeah, absolutely. So no air resistance. Any other assumptions?
I wouldn't
Now,
know.
assumption is that we're dealing with a point mass,
Uh-huh.
yeah, or a particle. We'll view these, we'll model objects or bodies as point masses or particle. A point mass essentially doesn't have volume.
Yeah.
Okay, so there we go. So maximum height above throw point is 27 meters. With what velocity was it projected? Do you want to have a try at that? Now, you can take G as being equal to 9.8 newtons per kilograms. Do you want to have a go at that one?
Yeah. Okay. Find that one. I rearranged the Suvat equation.
Yeah.
S equals v squared minus u squared over 2n.
Okay, good. So okay, you use that one then. So so you said S equals to
So yeah, so s equals v squared minus u squared over 2a. I
u
rearranged it.
squared over 2a. Cool.
V squared minus s times 2a.
V squared minus S.
Yeah.
Okay, just take your time on the rearrangement.
Yeah, I knew that seemed
Yeah, that one is sometimes
wrong.
easily. So you're right here. V squared minus u squared over 2a is absolutely fine. Okay, and I like what you're doing in that you're rearranging for actually make okay. You can do it that way, I suppose. So S equals. So what is it that you want to make the subject? What do you want to make the subject of your formula?
The initial.
You want to find the initial velocity. Ah, okay.
Yeah.
So remember, this also can be rewritten as if I cross multiply or if I multiply by 2a on both sides, yeah, that 2a and that 2a cancel out. So now I get v squared equals, or v squared minus u squared equals 2as. So far, so good.
Yeah.
Yeah.
And then
so v squared minus 2as equals 2u squared.
yeah, that's what I wrote. Yeah.
Is that what you wrote?
Yeah.
Oh, you were spot on. Sorry, then I didn't hear that part very clearly. Good, you got then and then. Okay, cool.
And then v is 0.
So V
V
is
is 0.
absolutely well done. The maximum there, V is a 0. Good. So that term disappears.
Yeah. And then I did 2as.
Yeah.
And then I square rooted it.
Yeah, and what do you get then as your final?
I got 50.9.
Just double check that. So
yeah, because that seems very
it's slightly off.
27. Oh, I see what I did.
Okay.
I see what I did. That was a mistake. I accidentally squared something when I shouldn't have. $23.
23 indeed, yeah. Okay, absolutely spot on.
I shouldn't have
So
squared that.
23 meters per second. Okay, good. Now, even for something like a little question like this, there are a few things that we can do just in terms of making our life easy, and that is just making sure that we lay out with all the right signs. So what I meant by signs being very important, now you may or may not have done this, but it is encouraged practice to do so, okay? I will use everything that is going upwards as positive and everything downwards as my negative. So I'm measuring my distance of 27 meters from the ground where I launch it. So this 27 meters is being measured going upwards. So this will have a positive sign. Now gravity, or the weight itself, but gravity in particular, we know acts towards the center of the Earth. So that's acting in a downwards direction. So my gravity, I will give a negative sign. Is that making sense so far?
Yeah.
Good. Now, if I use this formula, this says u squared is equal to minus 2as. And if I use that minus, the minus is still fine because my g is a minus 9.8. So that will make everything positive here, multiplied by distance, which is also positive. If I square root this now, I'll get an answer that's 23 meters per second, and the sign will be also, well, as in the sign will be okay to use in a square root sign because I have stuck to the convention. If I was not using that convention, then I would run a little bit into a problem. Yes, especially when it comes to square rooting. That's where you end up that you end up with negative numbers. And sometimes what students do is they just make it positive. That's not the right way to do it. But if you stick to convention, then hopefully those things can be avoided. Now, note here, there's just a bit of a question. When the velocity is 0, what is the value of the acceleration of this ball?
Would it, the acceleration, there's still the force of gravity is still acting on the ball.
Yeah.
And when a force is acting on something, then it accelerates. So is there still
You're absolutely right. Acceleration is constant and it doesn't here. G, you're absolutely right. Acceleration is still minus g. At no point in time of this ball's path does the acceleration change to less or greater than. It always is at minus g, no matter at which point it is. So you're absolutely right. Well done. Okay, so that is if we've got something that is being launched vertically. Now, the key thing to note as well is that there are symmetries with projectiles. So the time it takes to go to that maximum height is also the time it's going to take to come back down. So I could have had an extension here and added an extension to say how long might it take, for example, to return back. If you can find how long it takes to get to its highest point, you can times that by 2 to work out how long the overall journey would take. Okay, here's another one. Now this one here is just to, so similar-ish, but testing a slightly different skill this time. So we have here, this time around, an object, initial launch speed. So U is given as 45 kilometers per hour. Okay, so the question is, how long before it returns to its launch point? So this is doing something like this. Shot up vertically, gets to maximum height, drops back down. So how long before it returns to its launch point? And again, we can take G as per usual. for this scenario 2.
Return to its launch point that goes up and down. So I guess just time.
Pardon me?
So I did v minus u over a.
Okay.
I converted
u over a.
and I converted 45 kilometers per hour into meters per second. So I firstly multiplied 45 by 1,000.
Top man, excellent.
And then divided it by 60 squared.
60 squared, spot on. What did that give you?
Oh, okay. Let me see. It gave me 12.5.
So 45,000 over 3,600. The 2 zeros are gone. 9 into 36 is 4. Sorry, 12.5. Oh, you've already got it. Excellent.
Yeah.
12.5 meters per second. Spot on. Good. Okay. What did you do next?
And then I did 0 minus 12.5.
0 minus 12.5.
Yeah.
So you're taking your final velocity 0, and it's going upwards. So you've taken this as a positive sign. Yes. Yeah. Minus, you're absolutely right. Okay. Divided by, now then a is minus if we're using that convention we chose.
Yeah.
Yeah. And
I guess the minuses cancel out.
Absolutely spot on.
Yeah.
12.5 divided by 9.8.
And then I initially for that I got 1.27 for that, but then I doubled it.
Correct.
After.
Correct. What do you
get 2.55.
Absolutely right. 2.55 seconds. Yeah. For return journey. Excellent. Yeah. Well done. Super. So no problems there. Now let's look at something now that is being projected horizontally. Yeah. I've got this type of projectile motion. Now imagine I told you that I launched some particle here with a horizontal velocity of, say, 10 meters per second. Now the question is, what will the range be? Let's imagine here that the height is, we'll make numbers nice and easy, 10 meters. What would the range be if we wanted to work out the range that such an object would reach? Now, in this case, we have got two things at play. So if I drew motion of the ball at different stages, this ball has two components, if you like, or one component first to start off with, only horizontal velocity. But the fact that it is taking a parabolic shape must mean that there must be two components once it leaves that edge. You've got the horizontal component of velocity, and also you've got the vertical component. Now with time, this vertical component will start increasing because downwards there's an acceleration due to gravity, okay? However, the horizontal velocity, because there's nothing impeding, there's no force acting in this horizontal plane, that horizontal velocity is unaffected. But like I said, the vertical velocity will be getting bigger and bigger and bigger and bigger with time. So when we do SUVAT in a case like this, if they wanted us to find the range, say they wanted us to find what is the range, because the range is in a horizontal plane, it means really what we're going to concern with are the things that are acting horizontally. Because remember, we're dealing with vector equations, So the directions or the plane we deal with is very important. So if I wanted to find out the range, what might I start off with? Now, good practice, you probably do it, is to write out your SUVAT and do a SUVAT for the stuff that is in the vertical direction, and also a SUVAT for the stuff that is in the horizontal. So for now, we want to find the range. We're just going to stick with the horizontal stuff, just for now, okay? But we will fill in this nonetheless. So S, the distance, that horizontal distance, the range, we don't know that. What's the initial velocity? Well, the initial velocity is 10 meters per second. What do you say the final velocity, the final horizontal velocity is?
0, because it comes to a stop on the ground.
Not quite. So this is where it's very important to remember that horizontal velocity is constant.
It's constant, yeah.
Never changes.
So yeah, I guess it does like move after.
Okay,
yeah.
Horizontal velocity is always constant. If you're asked to answer the question why it is always constant, there are no forces impeding its motion horizontally. There's nothing acting horizontally to reduce the speed. Okay.
So will it just say that air resistance is negligible?
Absolutely, that one is key. So with that assumption still in place, the final horizontal velocity will still be 10 meters per second. What about the acceleration? What would you say?
That will be, there's no, is there acceleration? Well, acceleration and gravity is only vertical.
Correct. So in this horizontal plane, is there anything that's accelerating or acting to make it either horizontally or slower horizontally?
No.
No, absolutely right.
Yeah.
0. So horizontally is very, very easy because initial is the same as final all the time. All the time, okay? The time we don't know. What about vertically? Well, vertically, if I'm measuring my distances from the top, this distance here is minus 10 because I'm measuring downwards. The convention is very important. If I've decided that up is positive and down is negative, I'll stick to that, okay? What's my initial vertical velocity? Is this thing moving vertically initially?
No.
Oh, no
0.
vertical velocity. What is my final vertical velocity? Well, I don't know, but I know that the velocity is going to be increasing, that vertical. So this here represents, I'm going to use the symbol VV for vertical velocity, and I'm going to use the symbol VH for the horizontal component. So this stays the same, and VV here, by the way, is the vertical component of velocity. Okay.
Yeah.
Saying that VV increases as gravity, or if you like, the object, as the object is accelerating downwards. So downwards is an acceleration due to gravity. Okay. Final velocity, do we know what the final velocity is when this hits the ground? No idea. We don't know what that is. G, that's acting down. So I can say that that is minus 9.8. The time, we don't know the time. Now, the key thing to note is that these two times here will be common to one another. They will be common, because how long it takes to travel vertically is the same time that it will take to travel that horizontal distance. Does that make sense? Yeah. So now if I want to work out, the range, to work out the range, yes, what I need to do is I can use that formula. S equals U plus V over 2 multiplied by time. The U under the V are the same. Now I'm dealing horizontally here. So now I have 2U, they're the same, they're both 10, they're both the same number. Over 2, yeah, multiplied by T gives me, hey, S. So the range, the formula for the range will be given by VH multiplied by the time. VH, which is the horizontal component. Okay, and I'm going to label this as the horizontal component. So note here, Conrad, I'm using the horizontal component of velocity to work out a horizontal distance, which is known as the range.
Yeah.
I know what VH is, but I don't know what T is. How can I obtain a T?
I guess you could use, once you have, you don't need S, so you would use velocity, final velocity minus initial velocity over the acceleration. And you could.
The problem with that one is you don't know we don't know what.
Yeah, we don't know what.
So just looking at which solved equation would be able to help us out if we know distance or displacement, if we know initial velocity, and if we have acceleration.
Oh yeah. You. Where are the other? So bad with remembering all the different Suvat equations.
That's fine.
S equals, you could rearrange distance equals initial velocity times time plus half AT squared.
Correct.
So you could rearrange that for time.
You're absolutely right. Now, the beauty about this formula is the initial velocity here we've said is 0. So that goes 0 times time.
Yeah.
Yeah. So if I rearrange this now, I get 2 times S, I get 2S over G square root gives me the time. Yeah.
Yeah.
And now, again, because of my convention, this is minus 10 divided by minus 9.8. These again would cancel out in terms of sign, and I'd have a positive number. So to find the range now, my range is going to be given by the formula VH multiplied by root 2 S over G. And that is my horizontal range. So far, so good.
Yeah.
Excellent. Yeah. Now, sometimes what you tend to be given, I haven't quite plugged in the numbers, but we can plug in the numbers 2010 to root 2, 1.4 times 10. About it should be about 14 or so meters anyway. I think if you plug in the numbers, you get roughly something close to 14 meters around about there. I've just used a quick estimate in my head. Is that what you get?
If I put it in my calculator, initial horizontal 10. I think so.
Yeah, it's about that because
yeah,
14 approximately.
Yeah.
14. I know it's an approximate number there. Right. Good. Any questions so far?
No, it's good. I've got some good notes.
Brilliant. Now the next thing we're going to look at is these projectiles, which are launched at an angle. So when you have something launched at an angle, the examiners like having a field day with these as well. Now, remember, the reason why we've got this shape is because we have gravity acting. If there was no gravity, you would not have a parabolic shape. All right. So normally what we are generally given is we are given some initial velocity with which this object is projected, and it's denoted, or we can call it U. This will normally be versus some angle to the ground, which we can call theta. Sometimes it is an angle to the vertical, but rarely. Just read the question is my key tip on this one, in case the examiners decide to be a bit crafty and unusual. All right. So with this one again, we can get a host of questions that can come from these projectiles. So just going to say projectiles launched at an angle. Okay, so there we go. We might be asked again to find what the range is, but again, in this case, we have to, as per usual. So that's the range, by the way. This here denotes the maximum height. Okay, now, SUVAT. To write a SUVAT for each of these planes vertically, yes, well, there's a number of ways to look at it. It depends to which part we are going to look at. Are we looking at this halfway to its halfway point? Because if we're going halfway point, then the displacement is h. But if we're going all the way down here, then, but because this is symmetrical, it's okay for us to just look at half of it. Because anything that we do this half, if we want to work it out, we can times it by 2, can't we? Yeah. So
Yeah.
Yeah, for range and time and total time of flight and such. So just for now, we're going to say we're looking at h. So we're looking at when it is halfway. Pardon me. What's the initial velocity vertically? What would you say using what's here on the board?
The initial velocity vertically.
Yeah. So now you're going to have to resolve this speed, or this u. So if that's theta to the horizontal, what component, if this is u, what component is acting horizontally and what component would be acting vertically?
So gravity would be acting vertically.
Yeah, okay, let me just put some numbers in here just to make life easy.
Yeah.
Imagine I say that that's 10 meters per second, and I say that this is 30 degrees. What component of this 10 meters per second will be acting vertically? And what component of it will be acting horizontally? Because that is what I need to plug into these.
So cos so 10 cos 30
would be
degrees
would be horizontal or vertical?
Horizontal.
Would be horizontal. So I can say here that my horizontal would be, I'm going to use 10 is u, yeah, theta, or 30 is theta. So I'm just going to call it u cosine theta. Yes. What about the what about oh no, sorry, I've got to write this down here. Wrong.
Oh yeah, all right, so right there as well, yeah.
Okay. What about the vertical? What would it be?
Sine.
You're absolutely right. It would be sine, wouldn't it? Now, students make mistakes sometimes when resolving, especially when it comes to moments and all such. So it's good that we've started on the right footing here. Okay, so remember, we're only going halfway. So what would be the final velocity at that maximum height vertically? What would be its vertical velocity when it is at its maximum height?
Vertical velocity on its own maximum height. It would be 0.
Very good. Always at the maximum height, we always have 0 vertical velocity. Very good. So this here would be 0. Yeah. Now, if we go horizontally, what would the horizontal velocity be, the final horizontal velocity at that maximum height?
It would, the horizontal velocity at that, would it just stay constant?
Correct.
So
You absolutely heard me. You absolutely heard me. We never change this. These never change. Very good. Acceleration, 0. This is very much a usual script for horizontal, so it's not as bad.
Yeah.
Acceleration here is minus 9.8, which sometimes we can denote simply as minus g, and the time for the s horizontally is what we call the range. Okay, now time of flight, these two times of flight, remember, will be the same.
The same. Yeah.
So you can calculate time using this and use it in there, or use it, calculate it from there and put it in there. So these times are the same. Okay. So these are the main equations. So if I'm going to use the equations now and I want to work out either time, I would apply the same thing we did. The same thing we did. But what I'm going to do is, because I've just written out these formulas, we've already had to work on the SUVAT. The applications are the same pretty much, and also because we've looked at this horizontal projectile. What I'm going to do is I'll fire you some questions which are going to assess this part of things, and also some aspects of what we've covered on projectiles. And when we next meet up, I'll see how you fared, and we will possibly need another few minutes to complete this properly, and then we'll make a start on one of the topics, either moments or collisions. How does that sound?
Yeah, that sounds really good. Yeah.
Superb, super stuff.
Brilliant.
Conrad, I will let you have a lovely rest of a Thursday, and you've got a bit of time off for tomorrow as well. Enjoy the eat the buns and cheese or whatever it is that'll be coming your way tomorrow. For the best.
Yeah.
Right. Thank you so much. Any questions?
No, I've got some really good.
Oh, you got some
notes here. Yeah, great.
I will send you the board work as well, and also I'll send you the video and I'll send you some questions.
Thank you.
Super duper. Have a nice one. Cheers, Conrad. Yeah.
You too. Have a nice one. Bye bye.
Thanks. Bye now. Cheers. Good.